All right, hello everyone. I hope everything is going well for you right now. So, as far as scheduling is concerned, yesterday you probably took a quiz over all of the intro material. That material is not going to be on the test, it is just going to be just that quiz. And so, today is really the first start of the tested material in terms of kind of a bigger test that's going to cover multiple topics. And so our first unit, I guess, is going to be what we call biochemistry, which is the chemistry that's involved in living things. And so this very first lesson is just going to be an intro and just some basic review material over chemistry concepts. So with you guys being juniors and seniors, we did a little bit of this chemistry review when we were in biology freshman year. And you had a whole year of chemistry most likely either last year or the year before. So we're still going to teach it to you and go over it again, but hopefully it comes back to you pretty quickly. So why are we talking about chemistry? Well, remember that our living things are organized, and they're organized all the way from the atomic level, which atoms make up everything, living and non-living. They're going to be organized from atoms all the way up to cells, and then remember that organization continues and cells make up tissues, and that organization actually goes all the way up to the biosphere. And so this particular lesson or this unit is going to focus on the lower end of that organization. So we're going to look at the chemical level of organization, starting with atoms, so we need to know what they are, and then we're going to go all the way through macromolecules in our first unit of biochemistry. Now, just a basic kind of overview. So once again, this goes back to your simple chemistry concepts. These are things that you've been learning since middle school or maybe even before. But matter is anything that has mass and takes up space. And so we have three main states of matter. You may have learned that there were four. There's plasma, but we have our solid, liquids, and gas. And so anything that has mass and takes up space is going to be considered matter. Now, the things that are not matter are typically going to be energy and forces. So like light is a type of energy, heat is a type of energy, gravity is a type of force, magnetism is a force. And so I don't have a strong physics background, but what we're going to be focusing on are those things that are made up of atoms. And so atoms are the basic unit of matter, and of course they're going to be the basic unit of living things as well. They make up everything living and non-living. Now we can look at the atom in terms of two main parts. We have the nucleus, which is going to be in the center here. And then we have the electron cloud, which is going to be the energy levels that hold the electrons around the nucleus. And then we can also take that atom and break it up into three subatomic particles. We have protons, neutrons, and electrons. Now, the protons and the neutrons are what make up the nucleus of the atom. So protons are positive, and they're in the nucleus. Neutrons are neutral, and they are in the nucleus. So these two make up the nucleus of the atom. And here in a little bit, we're going to learn about mass, but the mass of an atom is going to be here in the nucleus with the protons and the neutrons. And these electrons are really, really, really tiny, even tinier than the protons and the neutrons. They don't really carry a lot of mass, but they are going to affect the charge. So electrons are negatively charged particles, and they're going to be found out in those different energy levels, or what we call the electron cloud. Now, if we use the term atom, anytime you use this word here, okay, an atom of oxygen, an atom of carbon, an atom of hydrogen, anytime we refer to it as an atom, atoms are neutral. And what that means is the positives, or the protons, are going to balance out the negatives, or the electrons. So anytime we are describing something as an atom, we know that the number of protons is going to be the same as the number of electrons. And so neutrons don't have a charge, they're neutral, and so they don't affect this charge in any way. Now, these atoms are the smallest unit of an element, and an element is a pure substance that we naturally find on Earth. It can't be broken down into other things, but a single atom is the smallest unit of an element. And so an element is always going to be composed of the same kind of atoms, and this is going to be determined by the number of protons in that atom. So one proton is always going to be hydrogen, 2 protons is always going to be helium, 6 protons is always going to be carbon. And so the protons determine the element that it is, and one atom is the smallest unit of that element. Now, if we're looking at the periodic table, which we're not going to spend a lot of time with it, that's more chemistry when you're taking chemistry, but just a few reminders. If we were to look at the periodic table, there's some important values on there. We have the atomic number, which is always going to be the whole number, and that number tells us the number of protons. So remember that the element is determined by the number of protons. So 2 is always going to be a helium atom. 3 is always going to be lithium. And so these atomic numbers are essentially the determining factor of what is the element. If we were to change the number of protons, we have changed the element that we are talking about. Now, also on the periodic table, you will find the atomic mass, and this is the decimal number. And the reason it's a decimal is because it's an average. Here in a minute, we're going to talk about isotopes, but the mass of individual atoms can vary. And so the atomic mass is the average mass of atoms for that particular element, and that's why you see that decimal number. Now, regardless of what that number is, it always is representing the protons and the neutrons that you find, okay? So we could round this off and just simply say that this is 4, and then we could use that number to determine the number of protons and the number of neutrons found in the atom. And then we also have the mass number. So once again, the atomic mass is an average. The mass number is actually used to identify isotopes. So this is where if we were looking at one atom of an element, not necessarily what we're looking at on the periodic table, but if we had one helium atom, you can see that the mass number is 4. Okay, the atomic number is 2, so this is our protons. And so what that does is that tells us that this particular atom has an atomic number of 2, a mass number of 4. So this particular helium atom is going to have 2 neutrons. We can just subtract to find the number of neutrons. Remember that atomic number is protons, mass number is protons and neutrons. And so this is just going to be a more specific number for one atom. And so the mass number is always going to be a whole number, and this atomic mass is going to be an average. So that's why you see the decimals on the periodic table, because there could be some heliums that maybe have a mass number of 5, and so when they average those out, this is the number that they come up with. Now, when we're talking about elements, in terms of living things, there are 4 main elements that make up over 96% of an organism's mass. Okay, we've got oxygen, which is O. If you don't know the symbols, you might want to write those. We have carbon, which is C. We have hydrogen, which is H. And then we have nitrogen, which is N. Now, there's a couple others that are also pretty significant in terms of the mass. We have phosphorus and sulfur. And obviously, if you look at this chart over here, there's a lot of other elements like calcium, potassium here, sodium and chlorine that are also relatively high. As we get into the smaller numbers, though, we call those trace elements. But if you look at the human body or in general living things, these are the 4 main ones that make up life. And as we move through this chemistry unit, we're going to get to a lesson on macromolecules, which are organic compounds. Well, organic compounds contain carbon, and every single one of our macromolecules are carbon-based. They either have carbon rings or carbon chains, and then attached to those carbon skeletons are going to be hydrogen. And then also attached to those carbon skeletons are going to be oxygen. And then in some of our macromolecules, like proteins and DNA and RNA, we're going to find nitrogen. And so that's why these particular 4 are going to be the highest, is because these are the main elements that are making up our macromolecules. Now, over here, this phosphorus, also commonly found in macromolecules. Sulfur, also commonly found in some of our macromolecules. And so that's why these particular elements are at the top of the list. Another thing I want to mention is these 2, oxygen and hydrogen. A very large percentage of cells is going to be water, and so we know that water is H2O. And so that's another reason why you will see both of these on this list. So for all the elements that exist, the 118, whatever that number was, 4 of them make up the majority of a living organism. And that's because they make up those macromolecules. All right, now earlier I mentioned isotopes when we were talking about mass number. And so what an isotope is, it's an atom or atoms of the same element that have different masses, And the reason they have different masses is because the number of neutrons varies. Now remember that the protons determine the element, so they are never going to change for a particular element. Okay, hydrogen is always 1, oxygen is always 8. But what can vary are the neutrons. Now, they're neutral in charge, so they don't affect the charge of the atom in any way, but they do have mass. Okay, so the mass comes from the protons and the neutrons. So if the neutrons vary from atom to atom of a particular element, what that's going to change is the mass. And that's why we identify them by their mass number. And so over here we see some isotopes of oxygen, oxygen 16, oxygen 17, oxygen 18. Now notice the protons is the same for each one. The protons never changes, but obviously the number of neutrons changes and therefore the mass changes, okay? This is not going to affect how the atom behaves, okay? That's determined by another particle, but it will affect the mass of that atom. Now sometimes we have what are called radioactive isotopes, or just short radioisotopes, and these are going to be isotopes that emit radiation. And the reason they emit radiation is, for whatever reason, their nuclei are unstable, which what that means is the protons and the neutrons don't like really being together. And so what they'll do is they're going to emit this radiation, either alpha particles or beta particles or gamma rays. And by releasing these forms of radiation, it allows them to get to a more stable state. Now, you've probably heard of radiation before, and more than likely radiation has a negative connotation because radiation can be very harmful. But we can also use this radiation that's emitted in small amounts. We can use it in imaging techniques like PET scans. We can also use it in medicine. We can use it as tracers and trace chemical reactions through the body. We can use it to sterilize things. But we use radiation in various imaging techniques to help us see body tissues and body organs, to kind of diagnose different conditions. And so even though radiation in general is bad, in very small amounts we can use them in beneficial ways in science. All right, next up is going to be our valence electrons. So we know that protons determine the element. We know that neutrons play a role in the mass. And now we're going to take a look at these negatively charged electrons. So the electrons are outside in different energy levels around the nucleus in these different kind of orbitals. And I imagine at some point in your education you probably had to put dots on circles like we see over here. Now we call this the electron cloud because these electrons are in motion and they're moving around, but they are going to be found in different energy levels. And the first energy level is going to hold 2 electrons, and then after that they're going to hold 8. And so these valence electrons are the ones that are furthest away from the nucleus. They're on the outermost energy level, furthest away from that positively charged nucleus. And so because these are negative, what attracts them and keeps them from just flying off into space is this positively charged nucleus here. And so the further away they are from the nucleus, the more loosely they're held and the more energy and instability they have. And so it's these valence electrons specifically, the ones that are on the outermost shells, these are the ones that determine the behavior of the atom. It's these electrons that determine whether or not the atom will bond with other atoms or which atoms it will bond with, as well as what kind of bonds will form. And so once again, that first energy level holds 2. So for hydrogen and helium, the max number that they need to kind of be happy is going to be 2. But for all of our other atoms that have more than 2 electrons, the valence number that they want to have is 8. Okay, because in order to be stable, in order to be quote unquote happy, the atoms want to have a full outer ring. And so remember that atoms are neutral. The amount of protons are equal to the amount of electrons. But what will happen is, in order to kind of fulfill that valence number, sometimes they will either lose or they will gain electrons. Now, keep in mind, protons aren't going anywhere. Protons are staying the same. Protons don't change. But electrons could be lost or gained between atoms. And so what happens is, if an atom, which was neutral, gained electrons, it now has more negatively charged particles. Or if an atom that was neutral lost electrons, it now has more positively charged particles. And so If electrons are lost or gained, we can no longer call them an atom because they're no longer neutral. We now call them an ion. And an ion, by definition, is a charged particle. And so there's two types. We have cations and anions. And so cations are positively charged. This is what's formed when electrons are lost, because when you lose electrons, you now have more protons. And anion is what forms when electrons are gained, because you've gained negatives, so now the overall charge is going to be negative. Now this is kind of silly, but the way I remember these is a lot of times people like cats. They like to watch cat videos, or they like kittens, they think they're cute. So I always tend to think of happy cats. Cats tend to have a positive connotation. And then anion looks like onion. A lot of people don't like onions, they think they stink. Personally, I like them, but a lot of times people have a negative connotation when it comes to onion. So I remember happy cats, cations are positive, and anion looks like onion, and onions can be considered negative, and that's how I remember these two terms. All right, now when these atoms kind of do things or interact with each other and lose or gain or share these valence electrons, what they do is they form chemical bonds. And so when they form chemical bonds and atoms join together, they're going to form molecules, which is any two or more atoms together, or they're going to form compounds. And these words are not completely separate, okay? A molecule could also be a compound, okay? And you can have one molecule of a particular compound, but there is a slight difference in that a compound is slightly more specific. So a molecule is any two or more atoms together. So anytime you have two or more atoms bonded, you have a molecule. The compound, though, must contain at least two different elements. So like over here, you could have like oxygen gas. Let's say these were two oxygen atoms. Oxygen gas has two atoms, but if you notice, they're both the same element, okay? So this would be considered a molecule, but not a compound. A compound specifically has to have two different elements. So this could represent water. You could have a hydrogen and two oxygens, and I'm sorry, I said that backwards. An oxygen and two hydrogens, H2O. And so this is going to represent two different elements, the two different colors, so we know that we have a compound here, okay? So you could have a molecule of water, but water is also a compound because two different elements make it up. So a compound is slightly more specific than a molecule. Now, there's two main ways that compounds can form, two different types. We have ionic compounds, which are going to form by ionic bonds, which involve ions. So that should be kind of easy to remember. And then we have molecular compounds, which are going to form by covalent bonds. And covalent bonds involve a sharing of electrons. And so now we're going to take a look at these bonds in a little more detail, okay? So ions, the root word there in ionic is ion. And so an ionic bond is formed from the transfer of electrons. So for each one of these bonds, I'm going to give you a keyword. And the keyword for ionic bond is transfer, okay? And remember, it is your electrons that are involved in bonding, okay? Specifically those valence electrons. And so ionic bonds form when electrons are transferred from one atom to another, forming ions. So when one atom loses, they're going to become positive. They're going to become a cation. And then if another atom gains, they're going to become an anion. And hopefully you know that opposites attract. So when electrons are transferred from one atom to another, they become ions. One will become positive and one will become negative. So in this case, sodium gave an electron to chlorine. Sodium becomes positive. Chlorine gained an electron, so it became negative, and now opposites attract. So this attraction between ions is essentially what forms an ionic bond. Now, this is how we form these compounds, okay? So these are going to be bonds within a compound, okay? Or we'll call them intramolecular. They are within the molecule, they are within the compound, okay? And so ionic bonds are relatively strong until you put them in water, and then they do break up kind of easily, okay? Our next type of bond, covalent bond, are actually very strong bonds. And the key word for covalent bonds is sharing. Electrons are shared between atoms. You could have one pair of electrons that's shared, you could have multiple pairs that are shared, but the key is that we're not losing or gaining here, we're simply sharing. And so what these atoms will do is they'll get close enough together that they can just share a pair of electrons between them. And this is what forms a covalent bond. And like I said, they're very strong bonds. Okay, we're going to see lots of covalent bonds in our macromolecules. Now the deal is, in a covalent bond, once again, the key word is sharing, but that doesn't mean that the sharing is always equal. Okay, it really depends on the atoms that are involved in the bond. And what it comes down to is that certain elements like electrons more than others. It's called electronegativity. And some atoms have a higher electronegativity than others. Now, one particular compound, or element, sorry, hydrogen, they don't really care that much about electrons, okay? Whereas other ones like oxygen and nitrogen, they like electrons more than other atoms. And so what can happen is when these sharing bonds, these covalent bonds form, sometimes the electrons are shared equally. And if that's the case, we call them nonpolar covalent bonds. They don't really have any particular area where the electrons are hanging out more, and so we don't get any type of poles in that molecule, okay? Now, sometimes that sharing is unequal, and that's because some atoms like electrons more. So I always give the example of like when my daughters were little, they might have a friend over, and let's say they had Barbies. They would share with their friends, but they wouldn't necessarily give their friend half of their Barbies. If they had 6 Barbies, they might give their friend 1 or 2 to play with, okay? And it's probably not going to be their favorite. So they're going to keep more Barbies toward them because they like them more. I also like to give the example of like chocolates, Dove chocolates. I love dark chocolate Doves. And so I'm a pretty nice person, and I would gladly share with somebody if there were other people in the room. But I may not give them half of my bag of Dove chocolates. I may give them 1 or 2 because I like them more than they do. And that's what happens sometimes in these sharing bonds, is that some atoms like those electrons more. And so what they're going to do is they're going to hold them a little closer, and that's going to lead to a polar covalent bond. So some electron or some atoms hold those electrons a little bit closer. And when that happens, it kind of gives them a slightly negative charge, okay? Wherever the electrons are hanging out more, it kind of creates this negative pole. And then wherever the electrons are being pulled away, it makes that region of the molecule slightly positive. Now, these are not ions. We're not losing, we're not gaining. But if one particular region of that molecule is hogging the electrons, they kind of get these very slight, weak charge regions, okay? So here's a picture to represent your nonpolar covalent bond. They're sharing those electrons equally between them, okay? Here we are, we're happy. They're going to be kind of symmetrical. All is well, okay? Now, on the other hand, if we have a polar covalent bond, one particular molecule is going to hog the electrons. And you can see that the electrons are hanging out closer to this end of the molecule and further from this end of the molecule. And so what happens is this region becomes a little bit negative, and this region becomes a little bit positive. And that's what these symbols are. They represent a partial charge, okay? A very common example of a polar molecule is water. So the oxygen likes those electrons way more than the hydrogen does. And so these electrons are hanging out a lot closer to the oxygen end, making the oxygen end of the molecule slightly negative, and then the hydrogen ends become slightly positive. Okay, so what we have here are weak charges. And that takes us to another type of bond, okay? A third type of bond that we're going to talk about is a hydrogen bond. Now, this one's a little bit different because it is intermolecular, okay? It is between molecules and compounds. Now, before, ionic and covalent, those were the bonds that formed within the molecule or compound, okay? So we call those intramolecular. They are forming the molecule, they are forming the compound. Hydrogen bonds specifically form between 2 different molecules and compounds, and they form between polar molecules. So here we have these weak charges, these weak positives, and these weak negatives. Well, just like in an ionic bond, opposites attract. But here we just have weak opposites. So the key word for hydrogen bonds is that they are very weak bonds because they are attractions between weak charges, okay? So that kind of negative area on a molecule where that hydrogen is, or the kind of negative area on one molecule is going to be attracted to the kind of positive area on another molecule. And so these hydrogens, because they don't just love the electrons as much, they typically are more positive. The other areas of the molecule are going to be more negative. Those weak charges attract, and boom, we have a hydrogen bond. Now I want you to notice they're always represented with dotted lines, okay? A covalent bond is always represented with a solid line that represents its strength, and then the dotted line represents the fact that it is weak. So because they're between weak charges, the bonds themselves are not going to be very strong, okay? Now, even though they're not very strong, it doesn't mean they're not significant. Hydrogen bonds are incredibly important to living things, okay? Number one, this is what forms between water molecules. And our next lesson is going to be all about the properties of water, and most of those properties come from the fact that these hydrogen bonds are what are holding water molecules together. You'll also find hydrogen bonds in our DNA. So we have two strands of DNA. They are held together at these nitrogen base pairs, and it's hydrogen bonds that hold them together. Now, why is that significant? Well, in order for us to copy DNA, we have to come in here and break these bonds. And we can't do that if these are really, really, really strong bonds. It would take a tremendous amount of energy. So luckily we can come in here and easily unzip and open that DNA molecule up in order to copy it. We'll also find hydrogen bonds in proteins. They help give rise to that special shape that proteins take on, and many other molecules that we'll find in living things. So hydrogen bonds are pretty significant when we're talking about biochemistry. And so just a quick summary of your bonds. So bonds hold atoms together. That's what's making our molecules and compounds. We could have a sharing of a transfer of electrons that forms an ionic bond. Okay, so remember there's my key word. Ionic equals transfer. We get ions that attract. Covalent bonds, the key word was share. Okay, two atoms are going to share a pair or multiple pairs of electrons. If the sharing is equal, we get nonpolar molecules that don't have partial charges. If the sharing is unequal, we get polar molecules that do have partial charges. And if we get attractions between those polar molecules, we get hydrogen bonds, which are a weak attraction between those weak regions of a polar molecule. And so these are going to be some bonds that form between molecules and compounds that are very weak. And the last thing we're going to talk about today are chemical reactions. So essentially this is when those atoms are making or breaking bonds, okay? Now over here you can see, and you learned this back in chemistry, there's different types of chemical reactions. At this point we don't have to know all these terms and what they are exactly, but I just want to do a quick reminder that we could synthesize something, which means we make something. We're joining atoms to make something bigger. We could have decomposition, where we're taking something bigger and breaking it down into smaller parts. We could have single and double displacement, which is where pretty much the atoms are just rearranging and changing partners. Or we could have combustion, where something's burning, right? You don't have to know these terms at all, but I just want to remind you that all we're doing in chemical reactions is making and breaking bonds, okay? And so what determines how these atoms react with each other goes back to those valence electrons. Remember that the electrons are kind of responsible for that behavior. Now that takes us to a chemical equation. So the chemical reactions are represented by a chemical equation. Of course, we have the element symbols, okay? Now the reactants of a reaction are always on the left. It's always what we're starting with. So we're always going to have an arrow, and reactants are always to the left of the arrow. It's what we are starting with. That could be more than one thing in the case of this reaction, or it could just be one thing if it was a decomposition reaction. The products are always going to be on the right-hand side, okay? It's going to be whatever we end up with. It's what is made or formed. And then those are separated by the arrow, which means yields or produces or forms. And then we also have these big numbers here that tell us how many of each of those substances that we have. So the main thing is reactants are on the left, products are on the right. We're going to take a whole look at metabolism and chemical reactions and enzymes in another unit. And so just kind of wanted to introduce that here. And that is going to wrap up our first lesson on chemistry. I hope that you remember some of that material, at least some of it, maybe all of it. We will be taking a quiz on this in the future. I'm going to come up with some kind of practice for you to do, but hopefully it is just a review. And if not, I hope you guys are learning that you may need to study for this class. We're going to be having our first test coming up. Remember that those tests count for half of your average. So please don't take the course lightly. Please be sure you are studying the material. And please let me know, or your teacher know, if you have any questions or concerns. I hope you guys have a great day, and I will talk to you soon.